Assalamu alaikum. Dear learners, I hope you are fine and doing great. This video is going to introduce you to the brain of the industrial automation processes, that is the programmable logic controllers. We are going to discuss every aspect of these very useful and important controllers in this and upcoming videos. So if you are trying to learn all about PLCs from the ground, you are at the right place. Therefore, let's go. To understand the programmable logic controller, we first must know that what kind of tasks are required by any controller in an industrial setup. I am going to present two representative examples only. However, there can be numerous, in fact limitless situations where industrial controllers are helping us out. So the first example is of a simple drilling machine that is required to drill a hole in the work part up to a defined depth. Primarily, there are three sensors or limit switches that can be used to control the working of the drilling machine in this situation. The first switch will signal the control when the drill bit reaches the surface of the work part so that the controller can turn on the drill rotation. The second switch will signal the controller when the required depth of the hole has been achieved so that the controller can retract the drill head. And the third switch may be used to detect the presence of the new work part so that the controller can initiate the drilling cycle. Look how binary sensors may be used to control the drilling process, and hence a logical circuit utilizing the signal from the binary sensors may be implemented. Another example can be of counting the number of objects passing on a conveyor and directing them into a packing case or to the other conveyor or whatever. The counter will count the objects and the controller will keep a close eye on the count. As soon as the count reaches the predefined number, the deflector may be operated to direct the next objects to some other box or conveyor. So these are some typical tasks that are required to be performed by an industrial controller. Typically, the controllers used in any industrial setups are microprocessor-based systems. On the shallow level, a microprocessor system will require a program that will instruct the attached peripherals that how they should respond when certain conditions are met. For example, a simple program can be instructions like if switch A closes, output to motor circuit that connects the output to the motor circuit so that it can operate. Similarly, other program lines may be added for other tasks as well. So a program is the logic that a microprocessor-based controller implements, and if you have designed the logic accurately, the control will not have any issues in controlling the attached devices or peripherals. The main advantage will come from the fact that the programs can be changed easily, so that the same controller can now control a totally different situation, provided proper inputs and outputs are attached to the controller. Well, a PLC is a special form of a microprocessor-based controller that utilizes programmable memory to store instructions and to implement functions such as logic, sequencing, and arithmetic to control the attached machines and processes. Although all microprocessor systems have these capabilities, but the strength of the PLCs come from the fact that these are designed to be operated by engineers and technicians who have limited knowledge of computers and computing languages. Therefore, easy user interface, electrical connections, and programming options are something that are not present in other types of commercial microprocessors. The term logic appears in the name because of the fact that PLCs are primarily used to implement logical circuits or operations. For example, if A or B occurs, switch on C and similar situations. Over here, A and B represents the inputs that can be anything ranging from switches to expensive sensors or timers or counters as well. On the other hand, C represents the output actuators that can be anything from a simple LED to a high HP motor or a pneumatic cylinder to a hydraulic press. All input and output devices are connected to the PLC using suitable means that I'll describe in a bit, and the program inside the PLC will help it decide which output to turn on and which to turn off. So from the outside, there are three important things that should be provided to a PLC: the inputs, the outputs, and the program. Changing the outside connections, that is the inputs and outputs, and or changing the program can allow the PLC to control a completely different process. And this advantage may not seem big today, but in the early days of industrialization, this was the biggest advantage the PLCs brought into the industries. Back at those times, the inputs, outputs, and the circuit connecting them together all have to be physically rewired to change the process, even if the change was quite negligible. But PLCs allowed simple change of program to achieve a completely different scenario without the need for any rewiring. And even if inputs and outputs are needed to be changed, then the easy-to-use interface of the PLC allows simple connections and disconnections of the devices with the PLCs that anyone on the factory floor can easily do. As the technology advanced a number of folds since the introduction of first PLC back in 1960s, it's quite difficult to see differences between microprocessor-based computers and microprocessor-based PLCs nowadays. All of you must have used a computer and might be thinking that whatever I have described till now as the feature of a PLC, your computer can also do it quite easily. Well, that's true, but the difference lies at the core of the microprocessor that is present in the PLC and your computer. The microprocessors used in your computer are optimized for the tasks of display and calculations, whereas the microprocessors used for PLCs are optimized for the tasks of control through logic operations and withstanding industrial harsh environments. This is the reason that microprocessor in your laptop costs much more than that of the PLC. However, if same logical operations are carried out on both, that is your computer and a PLC, then a cheaper microprocessor of the PLC can give tough time to your expensive higher generation computer's microprocessor. So if I can list the main features of a PLC, then the list will go on something like this. PLCs are rugged and designed to withstand vibrations, range of temperatures, humidity, and noise levels commonly experienced in an industrial environment. This is not something that a microprocessor of a personal computer can withstand. Furthermore, the input and output connections are already built in the controller so that we can easily and directly attach input devices and appropriate output devices with relative ease. As far as personal computers are concerned, you can attach various kinds of input-output devices with them, but you'll need some special and expensive intermediate circuitry or hardware to achieve that. And lastly, the programming languages used for PLCs are far more simplified than those used for personal computers. The reason being PLC is to be used by personnel who are not proficient in programming, but have fair idea of electrical and logic circuits. Therefore, the programming languages used in PLCs are directly related to the logic and electrical diagrams already being used by the technical staff of the factory floor. Although the features I have described might give an idea that PLCs are very simple and primitive type of devices, but it's not the case. Nowadays, PLCs, though having the said features, are much more powerful and evolved as compared to their predecessors. A typical PLC comprises of these components. At the center, the processor connects everything together. It takes input from the input devices through an input interface, reads the program from the program memory into which the programming device has placed the program, communicate with any other attached PLC or devices through the communication interface, and lastly control the output devices through the output interface. In addition to all these things, power supply unit directly supplies power to the input interface, the processor, and the output interface. In a nutshell, these are the hardware components that makes up a typical PLC. Let's briefly discuss what is inside each of these components. First of all, let's see what the processor is made up of. The processor unit contains the microprocessor or a central processing unit that does every kind of processing. That is, read inputs, write outputs, and interpret the control program. The CPU itself is made up of arithmetic logic unit that is responsible for performing arithmetic and logic functions, memory that stores necessary firmware required for running the CPU, and the control unit that controls the signal flow through the processor. Moreover, the processor is equipped with a clock that provides the heartbeat to the whole system. The heartbeat frequency dictates the speed with which the CPU can perform its work. Nowadays, the frequency of clock can be as high as several gigahertz. However, PLCs having clock frequency of around 500 megahertz are good enough to perform major operations on the factory floor. Lastly, there are the highways on which signals travel inside the PLC and the processor itself. These signal highways are called buses and are dedicated to carry only a specific type of information. For example, a data bus will carry only data from one component to the other, whereas an address bus will allow only memory addresses and addresses of other components to flow in it. The overall structure of a processor is shown in this figure. It shows the connections of CPU with other components like the memory, both RAM and ROM, the input-output interfaces, and the clock through appropriate buses. Look at how dedicated buses are used for different kinds of signals. Moving to the input-output units, in short I/O units, these units are the gateways for the signals to enter or exit the PLC. Every I/O unit has a unique address that depends on several things that I'll discuss after some time. These unique addresses are used to get information from the input unit and provide control signals to the output unit. Moreover, each I/O unit has built-in isolation and signal conditioning circuitry so that input devices and most of the output devices can be directly attached with the I/O units without the need for any additional hardware. Although there are different isolation techniques that are used in various electronics, however, the I/O units mostly make use of opto-isolators. Opto-isolators, also called optocouplers, are used to isolate one electric circuit from the other. Normally, it is done when two electric circuits are operating at different voltage levels and there is a fear that excess current may flow from high voltage circuit components to low voltage circuit components, hence inflicting irreversible damage. The isolators make sure that only signal or information is transferred from one side to the other. Furthermore, there are multiple options available on I/O units in terms of voltage and current ratings of the devices that may be attached directly with the I/O ports available on the I/O units. For example, an input module might have some ports that supports devices working on 240 volts, while some ports for 110 volts, 48 volts, and so on. This flexibility allows the technician or engineers to directly attach suitable input devices with the input module. The signal conditioning circuit inside these modules allow conversion from one voltage level to voltage levels required by the PLCs. Typically, all external voltages are converted to 5-volt digital signal, which is then provided to the processor. On the other hand, the processor generates 5-volt control signal, which are converted to appropriate voltage levels for different output module ports. Typically, digital and analog ports are both available on output modules so that the digital or analog actuators may directly be attached on the suitable port. Although input modules use optocouplers to provide isolation of the input module circuitry from the outside world, the output module normally rely on other isolation techniques. The major reason is that for input side, the signal coming from the input device is required, whereas on the output side, devices require high voltages and currents. Therefore, isolation devices capable of switching high voltages and currents are used. The simplest of such device is an electromechanical relay. It can easily switch currents of the order of few amperes. However, it relies on mechanical closing and opening of switches, hence are slow to operate. And as they physically provides isolation between two circuits, therefore they can withstand high surge current and voltage transients both for AC and DC circuits. The second isolation component that is normally used is a transistor. Transistors are considerably faster as there is no mechanical movement involved. However, they are not as rugged as relays. The transistor IC may burn up easily due to surge current and high voltages. Therefore, normally fuses are installed in series with such isolators to protect them in case of emergency. A device similar to transistor called triac is used for isolation of AC circuits because transistors are only used for DC circuits. Other features and limitations of a transistor and a triac are similar to each other. There are two ways in which an external device may be attached with the I/O module of the PLC. The first way is to use the I/O module as a source of power for the external device. That is, input or output module will provide current to the external device as shown over here. This configuration is called sourcing because of the fact that the I/O unit is acting as a source. On the other hand, the I/O unit may act as a sink as well. Therefore, in this situation, the current will flow from the external device into the I/O module that will act as a sink. This configuration is called sinking. Normally, manufacturers from USA, Taiwan, Japan, etc. prefer sinking configurations and hence provide sinking modules with their PLCs, whereas those from Britain and most of the Europe prefer sourcing modules with their PLCs. However, nowadays a number of major PLC suppliers like Siemens, Mitsubishi, Allen Bradley, they all provide both kind of modules. Therefore, you can choose the one that suits your wiring conditions. Moving on, there are two common types of PLCs as far as mechanical design is concerned. The first type is called brick type or technically single box PLC. This type is used for small programmable controllers and is supplied as a complete package that contains every necessary components. That is, the power supply, processor, memory elements, and the input-output modules. Typically, such single-box PLCs have up to 24 input ports and up to 16 output ports, along with a memory that can store around 60,000 instructions. These PLCs are ready-to-use PLCs and hence are preferred for small processes that require quick automation solutions. Although the idea of a brick PLC is to provide a fully packaged PLC, however, some manufacturers do provide brick PLCs with support of powered I/O expansion modules. Hence, if the need arises, a limited expansion can be done to these PLCs. The other type of PLC is called modular or track PLC. And as the name suggests, it has separate modules that may be attached with the main processor by mounting them on the rack. Modules like the power supply, processor, communication, and I/O modules are all separately attached to a rail that connects these modules with each other. Depending on the requirement, the modules may be added or removed. Typically, different kind of input, output, and memory modules are added to expand the PLC. However, it depends on the power supply module and the processor module that what is the maximum number of I/O and memory modules that can be attached with. Normally, to limit the number of modules that may be attached with the processor and the power supply, the rack is designed with that many slots only. So the rack limits the number of modules that may be attached. This figure shows the typical construction of a modular PLC. The rack is powered by the power supply, and now you can attach processor, communication module, and I/O modules. There are possibilities to expand the PLC beyond the given rack. However, it is normally not done because of the limitation of the processing power a certain processor has. However, sometimes additional processor may be attached to expand the PLC beyond a single rack. As the last thing related to the introduction of PLCs that I want to talk about is, I guess, the most important one, and that is how to program a PLC and what are various things we should be careful about. Well, for starters, PLCs doesn't come with a programming device. We need normally a personal computer or sometimes a handheld programmer to program the PLC. Once we have a programming device, the next thing we need is the software IDE that can help us in creating programs and communicating the program to the processor of the PLC. Well, anyone even a bit familiar with the programming know that there are several different programming languages and software IDEs for those languages, but it would be a relief for you to know that for PLCs there are only 5 standard languages, and furthermore every manufacturer provides its own software for programming and communicating with the PLC. For example, Mitsubishi has MALSoft, Allen Bradley has RS Logix, Siemens has Simatic, Omron has CX1, and so on. Note that different series of PLCs from the same manufacturer might require different software provided by the manufacturer. So there are sometimes multiple softwares provided by the same manufacturer. Most of these softwares give you the provision to use any of the standard PLC language for programming the attached PLC. However, some only allow working through a specific language. Moreover, these software provide diagnostic functions for checking whether the written program is correct or has any errors, network and hardware connections, testing and monitoring capabilities as well. So in short, you have to master the concerned software to fully program, control, and utilize the attached PLC. It doesn't matter on the type and manufacturer of the PLC that how it is processing its input through the program and updating its output as a result of the logic programmed in it. A PLC will continuously cycle through its program for as long as it is in the run mode. A typical cycle of the PLC starts by storing the status of the input and output devices attached through the respective modules. These statuses are stored in the specific area of the RAM reserved for input and output modules. Now the CPU will scan the memory addresses corresponding to input and output modules and will read the status of all the attached devices from the RAM. Now this information will be used in the program wherever required. Once the program has been fully executed, the status of the output devices are updated by the CPU in the input-output section of the RAM. After that, the output statuses are transferred from the memory locations to the output modules, and hence the attached output devices are provided updated signals from the output module. Once this is done, the cycle repeats. The total time required to complete this cycle is called the cycle time, which can vary from few milliseconds to few nanoseconds depending on the frequency of the clock of the processor, the size of the program, the number of input and output devices to be read and updated, and various other system functions that are running in the background continuously. This cycle is shown as a flow graph over here as well. So a PLC will be continuously executing this cycle for as long as it is in the run mode. Although PLCs from all manufacturers follow the process cycle I have just described, but every manufacturer uses its own format to read or update the I/O module. To read a particular input, the program has to tell the processor that which input should be read and or which output should be updated. For this, the processor has to know the address or the name of the corresponding input or output. The naming convention used by each manufacturer is different, and therefore you must be aware of that for using it in the program. For example, Mitsubishi and Toshiba name inputs starting with the letter X followed by digits that represent the module number and the terminal number, whereas the outputs are named similarly but the letter Y is used instead of X. If we talk about Allen Bradley, then the naming convention used by its PLC looks something like this. The first alphabet can be I or O for input or output, then a colon sign followed by a rack number, then a forward slash, and then the module number followed by the terminal number. However, Siemens used this format for naming the inputs and output. It uses I for input whereas a Q for output, followed by a byte number that represents the module number, then a dot, and at the end the bit number which represents the terminal. With this, I guess we are ready to start programming PLC using standard programming languages. Therefore, this is everything for this video, and in the next video, we will learn how to program a PLC using ladder logic diagrams, and then later on how the program can be loaded on the PLC and verified. Thank you and take care.